we have a sequence of diagrams and we are required to draw the fourth diagram in the sequence. In a sequence, every subsequent term follows from the one before. Therefore, if we are required to draw the fourth diagram, the third diagram is going to be of the greatest importance. By studying the first three diagrams, we realize that in order to form the next diagram, a quadrilateral, in this particular case, the quadrilateral is a square, is added to the present diagram, and each of the remaining vertices is assigned a thumbtack. There we have diagram 3 already. All we need to do is fulfill the particular requirements and we will have diagram 4. In order to draw diagram 4, we will take diagram 3 that we have on the slide and add another quadrilateral and the necessary number of thumbtacks to the remaining vertices. That is what we have right there now. That is diagram 4. Whenever we have a sequence, we need to know the rule that relates each item to the subsequent item. At every single step of the way, all we need to do is apply that rule and we will have the subsequent item. In order to find the number of sticks in the sixth diagram, let us make use of the fact that the number of sticks are in a sequence increasing by 4 each time. Now we are required to put information in this table that we have right here, but we also have instruction in the statements of the problem that require that we solve other problems that are in a way related to the table because everything is in a sequence and all items are related, but according to the information solicited, we do not have the particular row or column that specifies that we need to determine the number of sticks in the sixth diagram. So let us do that. Determine the number of sticks in the sixth diagram. Notice that we are going up by 4 each time. So the first one is 4 multiplied by 1. 4 times 2 is 8. 4 times 3 is 12. The sixth diagram will have 4 times 6, which is equal to 24. So according to the sequence, the sixth diagram will have 4 multiplied by 6, which is equal to 24 sticks. There we have it, 24 sticks. And we have another bit of information that is not directly inside of this table, but of course is related to the information that we have there. We are required to determine the number of tacks that are in the seventh diagram. So the number of tacks that are in the seventh diagram is related to the number of sticks that are in the seventh diagram. If we can tell the number of sticks in the seventh diagram, we can determine the number of tacks in the seventh diagram. The number of sticks may be found, so we need to determine the number of tacks. We may take the approach finding the number of sticks first, although that is not the only way that we can do it. So the number of sticks may be found by continuing the sequence by adding 4 each time. So in order to determine the number of tacks, we are determining the number of sticks first. They are related. So determine the number of sticks in the seventh diagram. That may be done by continuing the sequence. By adding 4 to 24, we get 28, or we may just say 4 multiplied by 7 is equal to 28. And here we have just an occurrence, not necessarily a general form of the rule that relates the number of tacks to the number of sticks. So if we have the number of sticks, we can substitute that into this form and we will arrive at the number of tacks. There we have just one occurrence of the formulae that we have here, right here. And all we need to do is, in the appropriate place, substitute 28, which is, of course, the number of sticks. Simplify the result, and we will arrive at the number of tacks. So 28, we may simplify this by a common factor of 4. 4 into 28 is 7. Then we have 3 multiplied by 7 is 21. Then 21 plus 1 is equal to 22. So let us do that first. 21 plus 1 is equal to 22. And we have an alternative way of finding that out. Alternatively, we could have made use of the fact that the numbers that represent the number of tacks are in a sequence that increases by 3 each time. Here we have it, increasing by 3 each time. So the first is 4, then the second is 4 plus 3 is equal to 7, then the third is 7 plus 3 is equal to 10, the fourth is, add 3 to that, 13, plus 3 we have the fifth, which is 16, and then eventually we get to the 7th diagram. And if we continue the sequence, we realize that we will actually get the number of tacks in the 7th diagram, which is equal to 22. These number 8 problems kind of remind me about the mental ability problems that we used to have when we were doing, not GSAT. GSAT is long after my time. When we were doing common entrance, we had math, English, and mental ability. The mental ability problems required that we make use of a lot of pattern, sequences, series. And I think that those mental ability problems ensured that anybody who left primary school for high school had that mental ability. But now we do not have anything in the schools that is analogous to the mental ability problems that we used to have. And sad to say, I think that has contributed to mental disability, because we find that at the high school level, some of the simplest things that we have in mathematics are baffling students, and they are not difficult in terms of the numerical requirements, but simply they require us to think. And I'm realizing that more and more the thought process is diminishing from among the youngsters as they go up into the high school. And I realize that more and more the ability to think is diminishing from among the children as they continue their way through school. When they get to the high school level, you find that they are afraid to think, they refuse to think, and they cannot think. They do not know how to think. they do not imagine that at a particular stage of the game anyone will require that they think. So I'm just saying this to say that the mental ability is sadly missed by Richard James and also by his colleague Gavin Edman of the Montego Bay e-learning, because he's having some difficulty realizing that it is more difficult for students to think about anything that they are doing. Now we will go to the table and we will complete the rows and columns that we are required to complete. Complete the row of 52 sticks by inserting the corresponding formula. So if we are going to complete this row, we need to insert the corresponding formula. That's not difficult. We realize that when we have 4 here, 4 there, 8, 8, 12, 12. Therefore, all we need to do is take one of these, recoin it for 52. Notice that in every case, the formula is the same with the exception of the associated number of sticks. No difference in this case. We need to make use of 52 sticks. So let us make use of 52 sticks. That's all there is to it. The formula may be used with 52 sticks in order to determine the associated number of tacks. We will opt to reduce the formula by 4. So 4 into 52, that's 13. 3 times 13 is 39. 1 plus 39 is equal to 40. To write the rule that shows how T is related to S, we may consider that the result is T, which is the number of tacks. The number that is always placed in the formula is the relevant value of S, which is the number of sticks. So to write a rule that shows how T is related to S, we may just recoin one of these. What we have here the values of S. When we work this out, we will get the number of tacks, which is T. Therefore, the value T is equal to, take one of these and insert S, the number of sticks. So we have T is equal to 1 plus 3/4 multiplied by S. We will continue with part C on the next slide. The number of sticks associated with 55 tacks may be found by using the formula. The number of sticks will be the unknown, which is n, and the expression equated to 55. So here we have already the number of tacks. We need to know the associated number of sticks. That may be found by realizing that let us call this a function, that this function is operating on S and the result is T. Therefore, whatever the number of sticks is, the formula is operating on the number of sticks and the result will be the number of tacks. So the result will be equal to 55. So let us put the one that we do not know, and we will call it n, into this formula, and equate that to the number of stacks, which is 55, and we will solve that equation in order to determine n, and n will turn out to be the number of sticks. Transpose by eliminating 1, then multiply by the reciprocal of the fraction. Finally, reduce the fraction by a factor of 3. Eliminate 1 by subtraction, we will end up with 54. So 3 over 4 multiplied by n is equal to 54. Then we will multiply by the reciprocal of this fraction on the right hand side. We will reduce by a common factor of 3. 3 into 54 is 18. Then we multiply 18 by 4, resulting in 72. After finding the associated number of sticks, we may place it in its appropriate place and also make use of it in the formula. So 72 goes right there, and we have 1 plus 3/4 of 72, and that's all there is to it. After the examination, I can remember asking one of my students, Gerard McIntosh, how he arrived at the answer, well, the answers, and he outlined some outlandish method. That is fine. The examiner did not suggest a sober method, only that we complete the table. They surely expect that candidates will use improvised methods that are just based on common sense. I think that Gerard's methods were excellent, as I prefer common sense to mathematical principles any day. If you are prepared to use your common sense, as I always say, is greater than mathematics. So, if you are prepared to use your common sense, as I always say, life is easier for people who are prepared to think. The expressions on the right hand side of both equations are equal to y and must be equal to each other. So we have y is equal to x squared minus x plus 3. Y is equal to 6 minus 3x. So first of all, this is y, this is y. If y is equal and y is equal to, therefore these two must therefore be equal. X squared minus x plus 3 is equal to 6 minus 3x. That is as a consequence of the fact that both of these expressions are equal to y. We may convert this into a trinomial, then solve the quadratic equation. Negative 3x plus 3x. Negative x plus 3x is positive 2x. Then we have a positive 3 and we have a 6. 3 minus 6 is negative 3. What two numbers multiply to give a negative 3? And when we add them, we get a positive 2. That will be a positive 3 and a negative 1. So x plus 3, x minus 1 is equal to 0. So x is equal to negative 3 or a positive 1. We substitute this into the second equation. We are attempting all the time to use the equation that will give us the simplest result. So introduce this into equation 2. So on the first count we will have 6 minus 3 times negative 3. So 6 minus 3 times negative 3. Negative 3 times negative 3 here is a positive 9. 6 plus 9 is equal to 15. Then we have 6 minus 3 times 1. So y is equal to 6 minus 3 times 1. Y is equal to 3. When x is equal to negative 3, y is equal to 15. When x is equal to 1, y is equal to 3. Writing the expression in the form suggested by the statement of the problem is a matter of completing the square. So we will go straight ahead and complete the square on this. Notice that we hardly ever get a problem in the CSEC CSEC that says by completing the square. It always says express in a particular form, and we can identify the form as a completion of the square. Therefore, it means that we need to complete the square. Take 4 as a factor of the first two terms. This will cause the coefficient of x squared inside of the brackets to be equal to 1, and the middle coefficient will be affected. It is like we are having a partial factorization by 4, and we are factorizing these two by 4. So 4 into 4x squared is x squared, and 4 into negative 8x is negative 2x. So we're taking a common factor of 4. In completing the square, we need to take half of the middle coefficient and square it. So let us take half of the middle coefficient and square it. Half of negative 2 is negative 1. When we square negative 1, we get 1. Now, by so doing, we can match the terms. 4x squared, 4 times x squared. 4 negative 2x, 4 times negative 2x. But we have what? 4 multiplied by 1. We do not have it up here. So we need to take away 4. Because we are introducing, by completing the square, this 1 that causes us to be able to say 4 multiplied by 1 is equal to 4. That's not here. Therefore, we need to take away 4 at the end. So compensate for that new term by subtracting 4. What we have inside of the brackets, that's a perfect square. X squared, when we square x, we get x squared. When we square a positive or a negative 1, we will get 1. However, we have a negative 2 here. Therefore, it has to be a negative 1. Negative 2 minus 4, negative 6. Second law in the manipulation of directed numbers. Whenever we add numbers that have the same sign, add the values, and the answer will take the same sign as the numbers that we have added. We need to determine now the minimum value of the expression. The minimum value will be that constant value that is outside of the brackets. So the minimum of the entire expression will be negative 6. The minimum occurs when the expression inside of the brackets is equal to 0. That is, when x minus 1 is equal to 0, anyone can solve that equation. X is equal to a positive 1, or just 1. This is our favorite. Well, good if it is our favorite, because in the last few years I realized that the CSEC examiners have increased the frequency with which velocity time graphs are being given. We first need to determine the value of x. Good. That is a little bit of a twist away from what we are accustomed to. We are accustomed to finding the acceleration. But now, the acceleration is given to us. And after the examination, one of my students, Gracia Davis, she was really excited about what she did with one of these examination problems, especially this one. She told me that she got the answer to be 20, but let's see if that is true. The acceleration in any stage is equal to the change in speed, which is on the y-axis, divided by the change in time, which is on the x-axis. And we are drawing analogy between the speed and the time axes and also the x and y axes that we are accustomed to. It is not actually x and y in this particular case, but we are just making an analogy. So the acceleration is the velocity or the change in velocity over the change in time, or the change in speed over the change in time. Speed and velocity are not the same, but we may use them interchangeably under these circumstances. There we have our lovely triangle with the velocity part here is what? Is 12, and the time part is x. We have the acceleration to be 0.6. What do? Acceleration is 0.6, velocity is 12 over x. Let's go back. Acceleration, velocity, time. Acceleration is given to us as 0.6. Velocity, we know, we can look at this and see that it is 12. The value of x we do not know. We make the substitution, then we will make the transposition. So 0.6 is equal to 12 over x. So x is equal to 12 over 0.6. By transposition, the x dividing here will be multiplied there. Then we will have to divide by 0.6. 12 divided by 6 is 2. 12 divided by 0.6 has to be 20. So 20 seconds, and Gracia Davis is correct. We need to determine the acceleration in the second stage of the motion. In the second stage of the motion, acceleration is equal to 0. The car is traveling at a constant velocity of 12 meters per second. Notice that all the time we have it outlined in Richard James Mathematics Resources that a horizontal line is a region in which velocity is constant, acceleration is equal to 0. What do we know about a horizontal line? It is exactly on 12. It is not going above 12, it is not going below 12. That means the speed is always 12. Not increasing, not decreasing. We have a constant speed of 12. When there is no change in speed, there is no change in velocity, acceleration is equal to 0. Right there. It is a very long time. I cannot remember how far back I will have to go in order to see a problem that requires us to determine the distance traveled in only a portion of the motion. Very, very long time since I've seen one like this. I'm kind of enjoying myself with this mathematics resource that I'm creating right now. The distance traveled in the third stage of the motion, or in any stage for that matter, is the area under the curve in that region. And I especially enjoy this problem for this reason. So the third stage of the motion, we need to determine the distance traveled in that region. And I know what will happen. Some students because of what they are accustomed to, may just go straight ahead and find the area of the entire trapezium and say that is the distance traveled. But the question is particular about what region, and it is in the third stage of the motion, that triangle that we are talking about. The area under that third region is the area of that triangle, and area half base times height. It's a right angle triangle, we have no difficulty with it. The area is in the shape of a triangle, should have said right angle triangle, with base going from 25 to 60. From 25 to 60 is what? 35 seconds. And whose height we have right here as 12. So the area is half base times height. So the distance is a half 12 multiplied by 35. Multiplication is commutative. We may put this in any order. Half of 12 is 6. 6 times 35. That will give us 210 meters. And that's all there is to it. Some of my students told me that they actually enjoyed solving this problem. Was it so easy, or as easy as they were saying? Angle XYZ is based on the fact that opposite angles of a cyclic quadrilateral are supplementary. They have a sum of 180 degrees. XYZ. XYZ. We have a cyclic quad as we have highlighted right there. We have a cyclic quadrilateral. Cyclic quadrilateral, four-sided figure with all vertices in contact with the circumference of the circle. That's a cyclic quadrilateral. Opposite angles of a cyclic quadrilateral add to give 180 degrees. If this one is 64, what do you know about the other one? We take 64 from 180 degrees, and the result is 116 degrees. Right. This is another one. Angle YXZ is the angle that is subtended by an arc at the circumference and is equal to the angle that the chord makes with the tangent. So the angle goes from one end of the chord to the circumference to the other end of the chord. That angle is equal to the angle that the chord makes with the tangent. So the angle that the chord makes with the tangent is equal to the angle that the chord is actually spanning at the circumference. So that angle is equal to 23 degrees. Wonder why I didn't put it inside of the circle. 23 degrees. In finding angle OXZ, we need to find OXZ. OXZ. So why do we have these angles showing? Because in order to find angle OXZ, we need to first make use of the fact that of angles subtended by the same arc, the one at the center is twice the one that is located at the circumference. Therefore, we need to determine first this angle. The one at the center is twice the one at the circumference. But that's just not for just any angle. It is for angles that are subtended by the same chord or arc. If they are subtended by the same chord or arc, the one at the center is twice the one at the circumference. And if this one is 64, then we know what this one is automatically. So 180 minus 64, and that is equal to 28 degrees. Now we may finish the calculation of the angle OXZ by making use of the fact that the triangle OXZ is isosceles. That one. So we may finally consider that triangle OXZ is isosceles, of which angle OXZ is one of the two equal angles. So this is an isosceles triangle, and OXZ is one of the equal angles. So this is equal to the one that is over here. If these two are equal, we know already two angles are equal, and then we have another one. All of those angles added together should give 180 degrees. Therefore, one of these angles will be calculated by subtracting 128 from 180. And after we have done that, we divide the result by 2, and the answer is 26 degrees, and each one of those angles will be 26 degrees. This is our problem, and of course we know exactly, just by looking at the diagram, we can tell that it has to be related to bearings. Here we have our north line, here we have our north line. On the basis that angles on a straight line are supplementary, find the value of x. We are asked to find the value of x right there. And we know, as we can see, that all of these angles are on a straight line. Find the value of x. On a straight line, they add to give 180 degrees. This angle x will be what remains after subtracting these two from 180 degrees. X is 76 degrees. Next, we are required to find the length, the distance PR. We have PQ is equal to 220 kilometers and QR is equal to 360 kilometers. Whenever we have two sides of a triangle and the angle that the two sides form, we may find the side that is opposite to the known angle, or just the other side, by making use of the cosine rule. We have two sides of a triangle and the angle that they form. The cosine rule may be used in finding the length of the side PR that is opposite to the angle. Two sides of a triangle and the angle that the two sides form, we may be able to determine the length of the side that is opposite to the known angle. Now, what we have done right here is divide PR by 10, and as a matter of fact, we have divided each one of the sides by 10, and that is done in order that the expression may be less cumbersome. We have less digits, a little bit easier to work with in terms of how large the physical expression will be. So the cosine rule, we square the unknown side, that is equal to the square of this one plus the square of the other one, 2 times this one multiplied by cosine of the angle that the two sides form. And that is a simple pattern that we may make use of. First step of simplification: square 22, square 36, then 2 times 22 times 36. In the end, we will add these two and multiply this by this one. It's just a matter of simplifying the result. I know that some students, they try to subtract 2 times 22 times 36 from this result. Then they multiply the result by cosine of 56. That is erroneous because we need to multiply and divide before we add and subtract. So we need to multiply these before we can subtract from whatever we get as the sum right here. Then finally, PR over 10 all squared is equal to 894. So we find the square root of 894 and the result is 29.9. But that is equal to PR over 10 because we have divided everything by 10 when we are doing the entire calculation. At the end we will multiply by 10 again. So multiply the result by 10, we get 299 kilometers, and that is what PR is equal to. The expression was divided by 10 in order that the figures on the right hand side of the expression would not turn out to be too large, making the expression too cumbersome. Multiplying by 10 returned normalcy in the end. In finding the bearing of R from P, it is beneficial to note that the angle that represents the bearing must be located at P. Let us therefore find the angle inside of the triangle that is located at P. We need to determine the bearing of R as viewed or taken from P. If we are taking the bearing from P, the angle needs to be located at P. Therefore, we need to make our calculation at P. The angle that we need to find, because we cannot just find all of this angle in one step, or any other angle for that matter that is located at P. We need to find the one that is associated with the triangle, because the triangle has the knowns and unknowns that are required for us to make all of our calculations. Therefore, we will attempt to find the bearing of R from P by first making use of the angle that is located inside of the triangle at P. In this particular case, we are using the sine rule. We have one side of a triangle and the angle that is opposite to it. The sine rule may be used in finding the angle at P because the side opposite to the angle P is also known. Now the sine rule make use of angle opposite side, angle opposite side. Therefore, if we can write a single equation with one unknown, we are guaranteed that we will be able to find that single unknown. So if we are talking about side and opposite angle, we must first locate a side, a known side, and a known angle that are opposite to each other. So we have this side and this angle are known and are opposite to each other. Then, in order to determine P by using the sine rule, we have to have one unknown. Therefore, the side that is opposite to the angle P also has to be known. Right, after that is established, we have only one unknown and we may go straight ahead to solve the equation. So sine of P is equal to 360 sine 56 over 299. Put that into your calculator. You get your answer in an instant. Sine of P is equal to 0.998, and if we have the sine, cosine or tangent of an angle, we know exactly how to determine that angle. Of course, we will make use of the inverse function that is in question. In this particular case, the inverse function in question is sine So sine inverse of 0.998, and that is equal to 86 degrees. The bearing is measured in a clockwise direction beginning at north. So let us show the bearing of R from P. Now, we need to determine the bearing of R from P. The line PR or RP is this one. Therefore, we need to start at P and we need to take bearing. That means we need to go in a clockwise direction beginning at north. So here we have north. Clockwise direction beginning at north, we go all the way like this until we encounter the line that goes from R to P, which is this one, and that is the angle that represents the bearing, that one. Therefore, as we can see, we have, let me take a look at that first. This is 132 and then this one is 86. So we put those together and we have the bearing of R from P. Adding those together, we get 132 plus 86. The bearing is inclusive of the angle that was there before, which is 132 degrees. And the other one that we have just calculated, 86 degrees. Putting those together, the bearing turns out to be 218 degrees. Number 11, matrices. The first part of number 11A, because we have A for matrices and B for vectors. So A, the first part, requires that we find the inverse of the first matrix. How do we find the inverse of that matrix? We take the reciprocal of the determinant and multiply by what we know as the adjoint. There we have it. The determinant is 3 times 4 minus 2 times 5. So 3 4s 12 minus 2 times 5 is 10. So that we will have a half. And we need to take a half of what we have here, which is the adjoint. The adjoint is formed by changing places with these two and changing the signs of these two. And that is why we have this as our adjoint. And that is equal to a half of 4 is 2, a half of negative 5 is negative 5 over 2, a half of negative 2 is negative 1, and a half of 3 is 3 over 2. That's all there is to it. Two of the elements in the matrix are equal to 0. That is this one. In finding A and B, that is what is required of us, we need only to multiply that matrix of transformation by the position vector of 1 point. Because we have this is equal to 0, this is equal to 0, we do not have to write an equation that consists of 3 2 by 2 matrices. All we need to do, since the problem is already simplified by having a 0 here and a 0 here, we may just multiply the matrix of transformation by any point or the position vector of a particular point. So we take this matrix of transformation here, we multiply by the position vector of 7 2, right, and what do we get? 0 7 A times 2. So we get 2A. Or we have now B times 7, 0 times 2. So we have B times 7 is 7B. Notice that this one will fall out. Notice that this one will go out. So 0 multiplied by 7, that's gone. A times 2, 2a. Then b multiplied by 7, 7b. And 0 with 2, that's gone. So we have 2a and 7b. And that is equal to the position vector of the image. So the result is equal to the position vector of the image. It is equal to 2, negative 7. So what do we know? Equating corresponding elements, we may be able to find the values of a and b. 2a is equal to a is equal to 1. And then we have what? 7b is equal to negative 7, so b is equal to negative 1. Before describing fully the transformation represented by the matrix M on the next slide, let us insert the values of a and b in their respective places. I'm just hoping that we did not have any difficulty seeing how we arrived at a is equal to 1 and b is equal to negative 1. So we have a is equal to 1, b is equal to negative 1, and we have 0 here and 0 there. And all we need to do is insert 1 and insert negative 1. And that's all there is to it. Recall that in deriving the matrix of transformation, the points 1, 0 and 0, 1 are written as the two columns of a 2 by 2 matrix and subject to the transformation. The resulting matrix is the matrix of transformation. The matrix of transformation is this one. How do we arrive at it? We take the matrix 1, 0, actually is 1, 0, 0, 1, but these points 1, 0 and 0, 1 are written as a column of the matrix rather than the rows. As a matter of fact, whether we write them row or column turns out to be the same thing, but we have to consider that we are talking about the position vector of one point, which is 1, 0, and the position vector of another point, which is 0, 1. Not only that, but the images are written also as the columns. So we have to consider that we are dealing with columns all the time. So we have, according to the matrix M, the point 1, 0 goes to the point negative 1, 0. And also what? Also the point 0, 1 goes to its image 1, 0. And where did we get these numbers from? Right here. So the matrix that we are talking about is 0, negative 1, 1, 0. This matrix, this point is transformed to 0, negative 1, and 0, 1 is transformed to 1, 0. Which transformation is responsible for that? As a matter of fact, the statement of the problem, or the requirement of the problem that we are taking a look at this stage, is that we need to write a full description of the transformation that is responsible for this matrix, or the one that this matrix is responsible for. So notice what's happening. 1, 0 goes to 0, negative 1, as we have right here, and 0, 1 goes to 1, 0. Which transformation is responsible for that? Will cause this one to come down here and cause this one to go down there. Let us cause the transformation to be more true to life. So let us do it again. The transformation is a rotation 90 degrees clockwise about the origin, because we can see that this has rotated to this one, and of course the one that was here before rotated to this one. So each one has rotated through 90 degrees about the origin. vectors. The figure is a parallelogram, therefore opposite sides are equal. Because it's a parallelogram, opposite sides are equal. So we have A is also here, and we have B is also there. So we have A, B. We have like that. Observe the movements that constitute the vector X, W, Y. Observe the movements, because we need to determine the vector WY. Let us take a look at the movement that constitute the vector WY. Find the vector WY. So WY, look at the movement now. A and opposite to the vector B. A and opposite to the vector B. So positive A minus B. That is WY. The vector WS is 1/3 of the vector WY. So WS is 1/3 of the vector WY. So WS is equal to 1/3 of the vector WY. Is there any other vector that we need to determine? The movement from S to X may be taken from S to W, then W to X. So S to X is negative of the movement that we have just calculated. So let us take a look at the movement required for the vector SX. Move from S like that, and then like that. So we move from S to X, from S to X, S to W, then from W to X. So S to W, W to X. Now from S to W is negative of the movement WS, because it is in the opposite direction to WS. Therefore, to move from here to go there, we have what? Negative 1/3 of A minus B. Then we have all of A. So SX is equal to negative of that and positive A. So negative 1/3 A minus B plus A. Now, if you cannot manipulate your fractions, you will not see how quickly we can arrive at our answer. We have negative 1/3 A. So negative with negative is positive. We have positive 1/3 B. So negative 1/3 A, positive 1/3 B, and we have A here. Now we have A minus 1/3 of A. We have cake minus 1/3 of a cake. We have 2/3 of a cake left. I guess that if we use something that is edible, the students will have less difficulty seeing how we arrive at the answer. So we have what? An entire cake minus 1/3 of the cake. We have 2/3 of the cake left. So we have 2/3 of A plus 1/3 of B. And do not forget that the whole cake is 3/3. And if we are taking away 1/3 of the cake, we will have 2/3 left. And SX is equal to 2/3 A plus 1/3 B. What are we required to do next? We are told that R is the midpoint of VW. So R is the midpoint of VW. Then we need to prove that RS and X are collinear. So R is the midpoint of VW as we have it right there. And then we need to prove that RS and X are collinear. In order to determine that R and X are collinear, or any 3 points for that matter, we need to form two vectors. that involve the 3 points and prove that they are parallel. We have the vector Sx already. We may now find another vector. So we need to prove that R, S, and X are collinear. We need to form two vectors involving the 3 points and prove that they are parallel. We do not have to go through all of that because we have one of the vectors already. Let's see which one we have. We have the vector Sx already. Because we have the vector Sx, we may find Rx or Rs. We will find Rx. What is Rx equal to? A half of B plus A. Do not forget that R is the midpoint of VW. So the entire vector is B. Therefore, from R to W is a half of B, and then all the way here we have A. So we have Rx is equal to a half of B plus A. We write the vector with the A component first and recall the vector Sx from the previous slide. So all we need to do is just write this, change it around, place the A at the front, and we have A plus half of B. Then we have what? 2/3 of A plus 1/3 of B. So we have Rx is A plus a half of B, and we have Sx is equal to 2/3 A plus 1/3 B. So we have these two vectors. All we need to do is show that they are parallel. Then we can say, or come to the conclusion, fairly, that all 3 points are collinear. If the vectors can be shown to be scalar products of each other, then they are parallel. And there's another way to show that they are parallel, if they can be shown to be scalar product of the same vector. So if the vectors can be shown to be scalar products of each other or to be scalar products of the same vector, then they are parallel. So for Rx, take a common factor of a half. So for Rx, let us take a common factor of a half. So half is our common factor, and for Sx, 1/3 is our common factor. I am sure that we can see quite easily that if we take 1/3 to be our common factor, we will have 2 and we will have 1. So we'll have 2A plus B. No difficulty. But when we take a half as the common factor here, we have what? 2A plus B. That is probably a little bit more sophisticated and unsighting. But we'll take a look at that on a subsequent slide and show beyond the shadow of a doubt that if we take a common factor of a half, we'll actually have 2A plus B. I am sure that quite a few students will have no difficulty seeing that. The vectors are scalar products of the same basic vector. They are therefore parallel. So they are scalar products of the same basic vector. This is 1/2 of 2A plus B. This is 1/3 of 2A plus B. They are scalar products of the same basic vector. They are therefore parallel. The two vectors that involve the 3 points are parallel. Therefore, the points R, S, and X are collinear. They lie on the same straight line. On this slide, we will demonstrate how, by taking a common factor of a half, the factor that is inside of the bracket contains the term 2A. Remember that in factorization, the first step is finding a common factor. In this particular case, we are taking a common factor of a half. Right, so we take the common factor of a half, and notice that we have the a half of B. What do we do next in factorization? In the next step, we divide each term by the common factor of a half. let us divide each term by a half. So in factorization, we take the common factor and we divide each term by the common factor. Divide each term by a half. After dividing each term by a half, what do we do? Make use of the fact that dividing by a fraction is the same as multiplying by its reciprocal. So dividing by a fraction is the same as multiplying by its reciprocal. And what do we know? Here we have 2a and the 2's will cancel there. So simplifying the first term, we have 2 over 1 is equal to 2. It's right there. And in the second term, the fractions will cancel each other. And we have b. So there we have proven that if we take a common factor of a half, then inside of the brackets we will have 2a plus b.